Okay, so we should go now. Sorry about the delay. The topic we start with here is non-relativistic fields. Okay, and the fact that we started with the relativistic ones is partially because we did that string which has the same notation as the relativistic one, but partially because it's a useful field. Here, the non-relativistic case is simple also. Let me just write out the Lagrangian for the Schrodinger equation, and then I'll show you that it works. It's I over 2 psi star d0 acting that way minus d0 acting the other way, so brackets psi. That's the Hermitian form where it's acts sort of either direction. Minus 1 over 2m del psi star del psi. Okay, and if I wanted to add interactions, the various things, let me just put this in brackets since I'm not going to carry it along. You could add minus psi star v of x psi. That also works. I'll show you. You clearly know where it goes in the Schrodinger equation. That we'll get out in a bit. Or you could add, much more commonly in field theory, would be to add an interaction there. So rather than a potential, you add an interaction with another particle. So the typical one that you see, and this is a condensed matter field theory one, you take some constant, psi star psi, psi star psi. You know, there's interaction of two particles with just a constant. It's a delta function interaction. Okay. So you could add those things if you wanted. And in condensed matter, you'll see a lot of that second one. Okay, so the way you're treated, remember these are complex fields, so psi and psi star for Lagrangian stuff are treated independently, just like phi and phi star were. And so to get the equations in motion, you'd do the following. You'd say, well, what's dl d time derivative of psi, d0 psi, that's the time derivative. That's actually, remember what we're going to call pi, the canonical momentum. And you can see, actually I want to do it first with respect to psi star. So let's put stars on that. And you'll be able to see the answer for psi's also. If I take the derivative with respect to d0 psi star, it sits right here. There's the derivative acting on psi star. So I get minus I over 2 psi as that guy. The derivative with respect to the gradient of psi star, well, that sits over there. That's minus 1 over 2m del psi. And the derivative with respect to psi star itself, okay, there's one place where there's psi stars without it. Derivatives acting on it, that's here times the derivative acting on psi. So that's I over 2 d0 psi. Okay. So then our equations of motion, remember in non-covariant notation, were the time derivative of dl d0 psi plus the space derivative of that with respect to grad psi minus the derivative with respect to psi itself equals 0. So the first term is the one that sits over there. They're actually in order there. So it's minus I over 2 d0 psi. And the second one is, minus 1 over 2m del squared psi. And the last one is minus I over 2 d0 psi again. Okay. Or then I d by dt of psi is minus del squared over 2m psi, which is the Schroedinger equation. And if I'd added a v psi, if I'd added this term here, there'd be the usual v piece there. Okay. So it's not, we've gotten that. Yeah, sure.
Where do we get all these Lagrangians? Do we just get?
Yes. So I'll actually provide a little better argument than just guessing, but in a minute. Okay. So that's my. After I do the Hamiltonian, I'll provide a little better argument. But in principle, it's not a bad idea. If you know what your wave equation should be, you're allowed to guess the Lagrangian. Okay. However, in relativistic theories, so that would work here. In relativistic theories, it's better in a sense. The action has to be Lorentz invariant. You shouldn't have a different action in different frames. And so your Lagrangian should be a Lorentz invariant. And so you're actually then very restricted in those theories to only write out Lorentz invariant terms. And in reality, what you're allowed to do is write anything that's Lorentz invariant and then see what the equations of motion follow from it are. Okay. So let's come back to the question. Thanks for the question. It's a good question. Okay. Let me just now form the Hamiltonian. Okay. One of the things that it's easy to see from this is if I had taken the variation with respect to psi, so I did this with respect to psi star. If I take it in respect to psi, we have just gotten the Hermitian conjugate of this, because this is an Hermitian Lagrangian. Psi and psi star enter as Hermitian conjugates. We have just gotten the Hermitian conjugate of the same equation, so there isn't anything worth doing for me. But to form the Hamiltonian, okay, the Hamiltonian by the rules that we've developed is sort of, it's pi d0 psi plus pi star d0 psi star minus the Lagrangian. We have pi star up here. This is minus I over 2 psi, sitting right up on the top there. You see on the very top line, pi star is minus I over 2 psi. If I had done pi, it's plus I psi star over 2. It's the Hermitian conjugate of the same thing. And the Lagrangian started off with, there we go. This guy starts off with I over 2, psi star d0 psi, etc. The point of looking at this is that the linear terms disappear. Okay, so I've got I over 2 psi star d0 psi, here I have I over 2 psi star d0 psi. The time derivative pieces disappear. If you carry it out, it turns into just equals del plus del psi star dot del psi over 2m. And then the Hamiltonian itself, the total Hamiltonian is the integral d3x. Well, what I'm going to do here, let me save myself one line. I've got this under the integration sign. I'm going to integrate it by parts and write it in the form that you'd be more familiar with, minus del squared over 2m psi. Okay, so I integrated by parts here. Take one of the derivatives, put it on the other side. But of course, you know, the usual form, you could have integrated by parts and put it in the symmetric form, the obviously Hermitian form. Those are all both equivalent. So that's the usual thing. And if I had carried the potential or the interactions around, this would have added either psi star v psi or plus u0 psi star psi squared to that. So you get your usual stuff. Okay. Fair enough. Everybody content? Good. Something familiar after all. Okay. So here's this alternate derivation that I wanted to show you. Okay. In this case, we're going to start from the relativistic case and find the Schroedinger equation as the non-relativistic limit of something that's relativistic. So this goes by the phrase non-relativistic reduction. Okay. Reduction here means you take something that's valid at all energies and you look at it in the low energy limit. So the case that I'd start with this complex scalar field d mu phi, complex conjugated, d mu phi minus m squared phi star phi. Okay, I'd want to use the complex scalar field because the psi is complex. Now, this is one here to answer the logic question. That form is basically forced on us by relativistic invariance. You have to d mu phi, and one of them should be upper. Okay, that gets forced on us by relativistic invariance, the fact that I use d mu phi. These are sort of the only things you could write down. You know, there's constants and derivatives. Okay? So there's a nice logical starting point. And then I'm going to let the following definition happen. Okay? I'm going to let phi equals 1 over 2m, root 2m, e to the minus I m t psi of x and t. Okay, and the idea of this is we take e to the minus I solutions of the form minus I e t and approximate those by e to the minus I m t. So the energy becomes the mass, the first approximation, plus dot dot dot. Okay, plus non-relativistic corrections. So we think that if we have something that is a massive particle, more or less just sitting there, let's start off with this energy dependence here. So it's a particle, mass m, sitting there with small motion, Okay. So the time dependence from e to the minus iet would just be the mass of the first approximation. Okay. So if you do that, then when you have d0 on phi, that's, well, this normalization 2m, there's going to be a piece that brings down minus im from taking the time derivative on the exponential. So I'll pull that out in front, e to the minus imt out in front now. There was the time derivative on the exponential, and then the other time derivative can act on phi. Okay. If that's the case, then Lagrangian is, well, there's a 1 over 2m everywhere from this normalization choice that I made. I get plus im plus d0 acting on psi star, or psi, yes, psi star, okay, times minus im plus d0 acting on phi. Okay, so that's the time derivatives. And the space derivatives become minus del psi star del phi, and then the mass term becomes minus m squared psi star psi. Okay, so one of the things I've done is this exponential that sits out in front here, because it was psi star psi, that disappears. Okay. So this is just a redefinition at this stage. Now, one of the things you see is the plus im minus im cancels the m squared piece, so m squared will disappear. There's a I over 2, the m's cancel that piece, times 1 time derivatives, and then there's a 2 time derivative piece. So let's just write out everything so far with no approximation. So this is just a rescripting. It's I over 2. I get psi star d0 minus d0 acting backwards. Psi, those are the first time derivatives. Okay, so this d0 times m, this d0 times minus m, and I get the minus 1 over 2m del phi. The m squared piece cancels, and I'm left over with a residual piece, which is plus 1 over 2m d0 psi star d0 psi. Okay? So the first pieces here are exactly the Schroedinger equation, Lagrangian, that we had before. So we've got that. And the last thing to do is just to say why the last piece disappears. This piece disappears because for this slow motion field, d0 psi is like del squared over 2m psi in the non-relativistic limit. And so this is like p squared over 2m. So this is p to the 4th over m squared. So this is a relativistic correction, p to the 4th over m cubed to the energy. So this is small, and you drop it. Okay? So, the point of this is to show you that the non-relativistic field is just the low energy limit of the relativistic field. The physics is continuous. All you've done is you've dropped small momentum as an approximation. Okay? Everyone content with that? Okay, if you're content with that, it actually tells us the logic of quantization also. Okay, if you're at small energy, you don't really have to worry about these antiparticle solutions. You don't have enough energy to produce them. So the logic of quantization here is just the following. You take the psi of x and you take solutions to it. You write this is sum over all the solutions, e to the minus I ENT times the solutions, which are the wave functions, times the creation operator. Okay. And let me, before commenting further, let's just do the continuum version. d3p over 2 pi cubed, e to the minus I ET minus p dot x. There's the solutions A of p. Okay. If you just do this and you plug into the Hamiltonian, remember, is the sum over, well, is the integral d3x psi star minus del squared over 2m. You know, maybe plus, let me put squiggle brackets plus v. If you want that, all this is the same, psi. That ends up becoming the sum over n, since these are energy eigenvalues, psi star n times this, whatever the Hamiltonian is, whichever one you choose, psi n, a dagger n, a n. So the Hamiltonian goes in there, either del squared or del squared plus v, which turns into sum over n, en, a dagger n, a n. So you get the same logical thing. This is what you see in quantum mechanics called second quantization. Second quantization is just non-relativistic field theory. Okay, and the only thing we've neglected here from the full relativistic case is we've neglected the existence of antiparticles. So in this formulation you don't have the antiparticles, but that's okay. You don't have enough energy to produce an antiparticle, so you never see it. You never lose it. That's the nature of the approximation. Okay? Comfortable? One of the things, if you're comfortable with that, one of the things you see is that after the fact, so after this, is if I take psi of x with psi star of x prime at equal times, at the same times. Okay, so I've got these two expressions up there, and I've got a's which have the usual commutation rules. At equal times, the time dependence drops out. You can sort of do those guys in your head. It becomes the sum over n of psi star n of x prime psi n of x. Or if in the continuum case, it's the integral d3p over 2 pi cubed e to the I p vector dot x minus x prime. Okay, so you can just do these. If anyone wants to do it in a little more detail, but it's just these commutation rules turn into A daggers and A's, which just give me 1. So I get the sum over the solutions, or the integral over momentum. If this forms the complete set, that is a representation of the delta function. This is obviously the delta function. So the commutation rules for the non-relativistic field are delta 3 of x minus x prime. Okay. So, little by little, we're stepping through all these guys. They each have a little wrinkle. Here, the wrinkle is that while the quantization looks like the same, the commutation rules are a little different in the non-relativistic limit. Okay. Next wrinkle. Okay, we're ready for another wrinkle. Let's do non-relativistic fermions. Okay, if you've seen second quantization, you realize that most of the time you're dealing with fermions, and fermions have a feature, a new feature, that their states anti-commute instead of commute. Okay, and here's how you see this. So we're going to take some creation operator. Okay, B dagger of P and a spin variable. Okay. The Pauli principle says, Pauli tells us that if we try to put two of these guys in the same state, so here's P S, B dagger P S. Okay, that's forbidden. Okay, so you can't do that. So that's equal to 0. Pauli also tells us that if you put them in different states, the wave function is antisymmetric. Okay, so it exists in different states. So let's now say I've got B dagger of PS and B dagger of P prime S prime. So they're different states. Now that's allowed, that's not 0. But the wave function has to be antisymmetric. And in this representation, the way you'd say it's antisymmetric is if I exchange the labels. So I take B dagger of P prime S prime, B dagger of P and S. So I've just exchanged the labels. That state should differ from the original one by a minus sign. Okay, it leaves all matrix elements unchanged, but that's the Pauli tells us these two things. So those two things can be put together into a single statement. The single statement is that the creation operators for fermions anti-commute. Okay, so if this anti-commuting symbol says AB is AB plus BA instead of commuting. Okay, so those two statements, this one is clearly just the same thing as that. I need a bracket there. And this one is consistent with it because if I put the labels the same, I just get this thing equaling 0. Okay. So our wrinkle here, our new wrinkle here, is to make fermions I use anti-commuting operators. And this then gets supplemented. Consistency seems to require that if I take B of P in S with B dagger of P in S, okay, that's not 0 anymore, that's delta P, P prime, delta S, S prime. Or in continuum notation, there'll be a Dirac delta function. Yes?
The primes are with the dagger first?
Yeah, so the dagger, well, they can be on either one, but I do need primes, thank you. Good.
Can we also have the possibility where we create a state with the same P and use different states?
Yes, that's right. Yeah, this is true actually for all P and S, and this one is also. So if I chose P equals to P prime, but S not equal to S prime, I'd still get 0. So yes, you can. I don't have to have the P's or the S's. Only one of them has to be different. Okay. Anything else? Okay, so it's a lovely little construction that then builds in the Pauli principle. Everything else sort of is the same. We'd still write psi of x and t in terms of solutions. You know, let's call it P and S, psi of P. X, wave functions times B of P and S. So you do the same construction as before. This ends up with the Hamiltonian giving you, again, the Hamiltonian then turns into sum over P and S, E of P, and principle that could depend on S, B dagger of P and S, B of P and S. Okay, free field doesn't do that, but if you put a spin-dependent potential in there, same thing would occur. Okay, the only residual trick is that instead of that commutation rule, it becomes an anti-commutation rule, psi of x and t, anti-commuted with psi of x prime and t. So this is the equal time anti-commutator. This is delta 3 of x minus x prime. Okay. So this is second quantization, but it's also non-relativistic field theory. Okay. Any questions about that? Ready? Ready? Then I'm on to photons. Ready for photons? Okay, photons. Okay, here I note that everybody but except this small cluster right in the center, Sebastian and our 4 students from Germany, have seen the material I'm about to present in the E&M class. And so I'm going to just do it as a review, okay? If you folks would like to chat, you can come and chat with me. If you'd like me to link the material that I used in the other class so you can take a look at it, I can link it into our class notes if you want that. You know, just let me know. Any of those options is perfectly fine with me. If people that have seen it want it linked so that you can review what I said back then, that's also fine. Okay, but here's the review. So wait till after the review to see how obvious it is to you. So in our notation that we'll use here, our basic fields are the scalar and vector potentials. And they fall into a 4-vector, A mu, which contains both of those fields. The E fields and B fields are derived. So these are the basic guys. Those are the things that enter the Lagrangian. The E and B fields are derived fields. Minus del phi minus d by dt of A, and B is del cross A. So these guys are derived. And in particular, they live in the following beast. The field strength tensor, so these are field strengths, d mu a nu minus d nu a mu. Okay? Okay, so those are the derivative operators acting on this field. And if you look at these guys, F0i, so one of the indices is time and one is space, so I get d by dt of a space guy or d by dx of a time guy. That gives me the E field. So that's minus EI. Okay, and if I look at Fij, okay, so F, for example, Fxy is d by dx of ay minus d by dy of az. That looks like del cross A. It's minus epsilon ij k bk. It's F is antisymmetric, so these are the only components of it. The diagonal components vanish. Okay? The equations of motion, which we'll get out, is that d mu f mu nu is 0, okay, which is, given this definition here, d mu is box on a nu, and then d mu on the second one is slightly different, so it's box a nu minus d nu d mu a mu. So that's the equations of motion. We typically will choose Lorentz gauge wheel. In this class, I'm pretty sure we'll always do this. Which is d mu a mu is equal to 0. Or again, d by dt of phi plus del dot a equals 0 to write it out. Then this thing turns into box a nu equals 0. Okay. The Lagrangian. The Lagrangian is minus a quarter f mu nu, f mu nu. It has to be relativistic invariant and gauge invariant, and f mu nu is a gauge invariant. That I haven't shown here. So I guess I have a chance to talk about that later on. If you plug this in, this is 1/2 e squared minus b squared. Okay, and the one point that I do need to point out for people that have particularly good memories from E&M is the units are different here. The units here are Heaviside Lorentz. And it really is much, you don't have to worry about this very much. But the the Hamiltonian, or the energy, well, I'll call it the Hamiltonian, but that's what I'll call it below, in this unit is 1/2 e squared plus b squared, whereas the Gaussian units that we use before would have been 1/8 pi e squared plus b squared. Okay, so there are the units that you see in the E&M class have these funny factors of 4 pi. They're cleaned up here, and it's much more analogous to every other field. Okay. All right, let's do the equations of motion. Okay, the equations of motion, remember, should be, here's what they are. They're d mu partial L respect to d mu on the field, which is a nu. I can put it. Minus dl dA nu equals 0. Okay, now, right now, with no interaction, there is no second term there, because the only things that depend on are on those guys. And, there's my Lagrangian right there. Okay? So, my variation there's a counting factor that is tough to explain here. So let's I don't know. Maybe I won't explain it. I'll hand wave it real quickly. F mu nu is derivative on the field minus the antisymmetric piece. Derivative on the field minus the antisymmetric piece. There are then 4 terms in that. When I take that variation, I get rid of the factor of 4. So it's minus 4 times 1/4 F mu nu. I can do that factor of 4 if you want. Okay. But if you
Is it because the four-dimensional?
No, it's because the, so let me write the Lagrangian, let me take one step. Let me call this my, remember these indices are dummy indices. Okay, they're summed over. So F, mu and nu are summed over. So in writing it out this next time, I'm going to do it as with a different label. I'll write it alpha A beta minus D beta A alpha times D alpha A beta minus D beta A alpha. Okay, so there's my thing. And now I'm supposed to come along and take the variation with respect to d mu A nu. So let's just mentally put, oh, I don't know, mu is equal to 0 and nu is equal to 1. Okay, so in this sum here, I'm supposed to pick out the piece where there's a d0 on A1. There's going to be 4 places that occurs. Well, okay, so in this sum times this piece here, so this piece here, there's a term where this is d0 and that's A1. So I take the derivative with respect to that and I get F01. There's also a term in this sum here where this is d0 and that's a1. I mean, so beta is 0 and that's 1. So I take that derivative, I get f01 again. So that minus sign there changes. That minus sign is d0a1 minus d1a0. Okay? In the sum, there's also one here and there's one here. So there's 4 separate terms where there's a time derivative acting on a1 buried in this summation. So that's the factor of 4. It comes from 2 times 2. It's not 4 dimensions. Okay, people see that? Okay, that's where it comes from. If you buy that, then the equation of the motion is then what is Maxwell's equations, or the equation of motion there. Okay, fair enough. And last thing I want to do for this is the Hamiltonian on the formal part. Okay, the Hamiltonian there's a little wrinkle here too. So remember, we're instructed to take the variation of Lagrangian with respect to d0 times your field. Okay, so now I've got 4 fields. Previously we had 5 there. Now we've got A's. A could be any of them. So there's actually 4 of them here. Pi nu is defined as that. And we've actually worked that out up there. It's minus f0 nu. Okay. Now here's a funny feature. This is 0 for nu is equal to 0. So that's the field A0, which is equal to the scalar, the scalar potential. And it's equal to EI for nu is equal to I. Okay? So this is the first wrinkle. But let's just follow our noses for a moment. If we follow the noses and take the Hamiltonian as pi nu d0 a nu minus the Lagrangian. Okay. That's equal to then I have to get my signs right. So it's minus EI times D0 AI. So the new piece vanished, the 0 piece vanished. D0 AI. So I'll just write that. D0 AI. And I'm going to do the following. I'm going to subtract del phi and add del phi. Minus 1/2 e squared minus b squared. Okay. D0 AI plus del phi is minus EI. So the there's part of this here that becomes e squared, e times e, minus a half e squared. So the first pieces go into 1/2 e squared plus b squared, which is lovely. That's the energy density. And the only little complication left over is I have a minus plus EI grad phi. So there, we just use vector signs. There we go. Okay. And okay, the treatment of this last guy. So the first piece is what we know and love. That's great. This piece here is a little bit of a gauge complication. The way you deal with it is you integrate by parts. So we imagine that we're forming the full Hamiltonian. If you integrate by parts, this becomes phi times minus del dot E, which becomes rho. Okay, there's no 4 pi's in these units. And so this thing turns into rho phi, which is also part of the energy. So that's good. That's part of the energy. That's the energy of a charged particle. However, at the moment we're dealing with just the photon by itself, so here it's equal to 0. Okay, so you could imagine using the equation of motion to get rid of it. It's a little bit more complicated when you have not only photons but also matter in the same Lagrangian. Then you have to work on this thing a little bit better than that. But it's the same trick you use. Okay. Anybody? Okay, so now the people that haven't seen ENM, there's the stuff that you haven't seen. If you're comfortable with that, we'll go with it. If you want reviews or anything, ask me. Okay, at that stage we're ready for quantization. And quantization actually is in principle quite subtle. It's really only done right in path integrals. Okay? In the end of the day, that's where it's done. However, the results turn out to be very simple and intuitive. So I'm just going to give you the results. Okay? Okay. So here's how you quantize. We're basically trying to solve box A mu is equal to 0 with the condition that we're in Lorentz gauge. Okay. The solutions are easy. A mu is of the form some polarization vector, which is labeled by lambda, e to the minus I p dot x. So plane waves with a polarization, okay, and this conditions turn into then p squared equals 0, so e squared minus p vector squared equals 0. So that's the usual massless photon. And p mu dot epsilon mu, that's the condition that it's transverse. So that comes from the Lorentz gauge condition. Okay. I guess, to be honest, I should really label that by P and lambda, since it's, let's put the P in there. The polarization depends on the direction P, because it has to be transverse to it. Okay? So there's two polarizations transverse to the motion. Okay? So how would we do the quantum field? Well, you do the quantum field A mu of x and t is integral d3p 2 pi cubed 1 over the square root of 2 omega p epsilon mu of p and lambda e to the minus I p dot x a of p and lambda plus the complex conjugate. A dagger. Okay, it's a real field. So there's how you'd write it out. So at this stage, you could be doing classical mechanics still, and this is the most general expansion you get. Except now we know that we're going to do quantum fields. So if you take that, you take the usual commutation rules on these guys, and you calculate the Hamiltonian, which is the integral d3x 1/2 e squared plus b squared. Okay? And you know how to get E and B from that. And it's actually a lengthy calculation. You have to take, for E you have to take time derivatives and space derivatives. For B you have to take del crosses. You've got this polarization vector. You've got two d3p prime with a delta function there. There's various delta functions. These epsilon tends to satisfy various identities. The answer turns into, after the dust settles, d3p over 2 pi cubed omega p a dagger of p lambda, so there's a sum over lambda 2, a of p and lambda. The energy doesn't depend on lambda, where this is just the magnitude of p, and there's a 0-point energy, which is 2 times the 0-point energy of a scalar. So it's just 2. And it's basically, the 2 comes from sum over the 2 lambdas. Lambda, for each p there's 2 lambdas. So you get one plus the other of a half h bar omega from each of them. Okay? So this is then a good quantization. It's not that it's okay. So there we've done it. Yes, awesome.
Box in will be not equal to this, and then going to put the whole coil in.
Okay, so basically, when we write out the Lagrangian of the world, it'll be E and M plus a lot of other stuff. Okay. You'll write out the Hamiltonian of the world too. The Hamiltonian of the world will have E squared and B squared. It'll have the matter pieces. It'll have interaction pieces. And the way one does that is one neglects all the interaction pieces. So let's say there's something proportional to the electric charge over here. You neglect all those terms, and you individually quantize the E fields, all the different matter fields that sit in your Lagrangian, and they all have this formula. So we're doing the free field quantization right now, and then we'll turn on interactions soon. Okay? Okay? That's how you deal with it. You'd write the whole Hamiltonian of the whole system all together and show that it has this piece plus this piece plus interaction. Okay, anybody else? Last thing to say is just that if you also recall this pointing vector, Okay, the Poynting vector in these units is E cross B. Okay, and the equation of continuity is that the Hamiltonian density's time dependence plus del dot S equals 0. This is, by the usual tricks, tells us that the integral of the Hamiltonian density is conserved, so this is conserved quantity. This tells us that S is the flow of energy, and so the way the energy changes, the energy density changes if the energy flows away. That's what happens. Okay? And if you calculate the following, so if you calculate, we'll call it P, is the integral d3x of E cross B. And you do the same thing. You write A in the form that's sitting up at the top there. You write E and B in terms of the derivatives of that guy. You plug away through the night. You get sum over lambda integral d3p 2 pi cubed p vector a dagger p and lambda. The Poynting vector turns into the momentum flow. Okay, if you were to go back and restore units with c not equal to 1, the momentum flow actually is 1 over c squared times the Poynting vector. There's a factor of c squared. But here, it's much easier to remember that just the Poynting vector is the flow of energy. Flow of energy is just the momentum. Okay. So I guess the logical place for me to stop is here. Oh no, I have one more thing to say. Sorry, flip the page and just in time to. I have to tell you the propagator. Prop. Okay. Just like we had before. Remember, we had I df for the fermion, for the bosons was 0 time ordered product of phi of x, phi of y. Here we will have encounter things time ordered product of a mu of x, a nu of y, 2 photons. So it's df mu nu of x minus y. Okay. Now there are, again, gauge subtleties associated with this. And I'm not going to go through them here. I'll just tell you the answer. The answer that when everyone encounters this, it's the integral d4q 2 pi to the 4th. Now, leave a little space there. It's I over q squared plus I epsilon e to the minus I q dot x minus x prime. Okay, so that's what we had for df above, the scalar one. What you do for the photon, well, you need something that has a mu and a nu in it. Okay? The only obvious thing that's left over is g mu nu, the metric tensor. And it's actually a minus sign. And the minus sign comes from the fact that the physical guys are really the spatial pieces. If you went and looked at the transverse, the things that are transverse to the motion live in the spatial direction. So they're pointing, it's moving in the z direction, epsilon points in the x direction. So minus g mu nu is a positive number for the space directions. The the thing that's not at all obvious, which I won't do today, is that this not only contains the real photons, meaning these two with two physical polarization, it also contains the Coulomb interaction. Okay, and I guess what I should do is, given where we are in time, I'll tell that story at the start of class next time. I'll show you how this gives the Coulomb interaction. And talk a little bit about the gauge complications that I'm, for the most part, just waving my hands about. Okay, let's stop there. So, my exchange students, have you seen this relativistic formulation of this before? Yeah. So you saw F B news is perfectly good. All right, good. If you want anything, that's